So our next speaker is Thomas Hertog. He will talk about quantum gravity in de Sitter space. Again, the same title, but from different viewpoint. So yeah, the floor is yours.
Thanks. Good. Yes, same title, different subject. So I'd like to report on two recent results on quantum gravity in de Sitter space that have to do with the quantum behavior of the background. So whereas in the previous talk we heard a lot about the behavior of the fluctuations, I'm going to be focusing on the quantum behavior of the background. These are the two papers. The first one is a recent paper that I wrote with Oliver Janssen at ICTP and Joel Carlson, a PhD student in Leuven. And in fact, we dedicated this paper to the memory of Jim Hartle, not only because Jim was a good friend, but also because the paper is very much a continuation of the subject that he pioneered together with Hawking in the 80s. As you might know, Stephen and Jim wrote this famous paper, which essentially launched the whole subject of quantum cosmology in a way we understand it today. So the grand idea that came out of that paper in the 80s is, the idea that besides the theory of dynamics, the universe as a quantum system probably also has a quantum state. And we should remember Jim, I think, as really the father of that field, quantum cosmology, that came out of it. And so what they advocated for years and years really was the idea that, okay, that quantum state is as much a part of a final theory as the theory of dynamics. So what is the quantum state and what can it do for us? Well, as you know, they had a proposal in the paper which became known, or which they refer to as the no-boundary proposal, the no-boundary quantum state for the universe. And they were inspired really by simply the idea of the ground state of the harmonic oscillator, which you can express in Euclidean terms. So they wrote down this equation for sort of a Euclidean path integral formulation for the quantum state of the universe, without being able, of course, to tell us precisely what exactly are the degrees of freedom, what does this path integral mean. But as a saddle point approximation, what comes out of their thinking is really the idea that we should be looking not just at the usual expanding spacetimes, but that we should be looking at complex saddle points as the quantum mechanical backgrounds for cosmology. And that's sort of sketched here. The crux of their proposal was that an expanding de Sitter-like universe at late times, up there in the picture, emerges from a complex or a Euclidean no-boundary saddle point. So down at the bottom, space-time behaves more or less Euclidean. The crux of their no-boundary proposal is that there's no boundary, of course, at the bottom. Down at the top, the space-time behaves Lorentzian. And that simple idea, so turning time essentially into a space dimension, that simple idea comes with a number of key predictions. The one prediction on the left there is that our usual FLRW expansion, classical cosmological evolution, is an emergent property in that quantum theory, and it emerges in a specific way, and it emerges through a phase of a de Sitter-like phase, a phase of inflation. You can only get, when you require there to be regularity, when you require there to be no boundary in the past, a regular compact Euclidean spacetime, well, that essentially implies for you an early phase of inflation. So it's a sense, it's theory of the origin, a quantum theory of the origin of inflation. Next on the right, the condition that space-time behaves regularly all the way at the bottom in the quantum regime where the geometry is Euclidean also implies that the fluctuations are small down at the bottom. If the fluctuations are small initially, it essentially implies more or less a Bunch-Davies vacuum state and therefore an arrow of time when you move up. However, as you know, there are many different models of inflation, and some people say this is a success. Others say, well, the theory doesn't quite agree with observations. It can be scattered all around. So you can read this famous Planck diagram in two different ways. And so for a long time, Stephen, Jim, and I looked at this and wondered whether the no-boundary theory of the quantum state could refine the predictions of inflationary theory. So can the no-boundary proposal be a prior that essentially would zoom in on one or another part of this picture and therefore strengthen or refine the predictions of inflation? That's ultimately what you would want from a quantum theory. But it's complicated. It's complicated for various reasons. The first and obvious reason is that any prediction that you might want to derive from a wave function of the universe involves a conditional probability. Just like an electron in quantum theory doesn't have a position before you ask it, well, the universe doesn't quite have a definite history before you ask your question. But the questions we're asking in cosmology are very detailed and complicated and involve a lot more than just thinking about the wave function. The second problem is equally obvious. As I already alluded to, we don't have very much control over the path integral. We have a saddle point approximation. We have no clue about the underlying microscopic degrees of freedom. So what exactly is that path integral, that wave function? And as long as we don't quite know that, the predictions are bound to remain a little vague. And so the two papers that I briefly want to report on are two recent results that go in the direction of refining that theory. So the first one is the one that I already mentioned. What do we do here? Well, Kontsevich and Segal a year or two ago came up with a criterion that would further restrict the use of geometric saddles, complex saddles in field theory. Really, there was their motivation, but then Witten later extended their criterion or sort of elevated their criterion to a selection principle of saddle geometries in gravitational path integrals. And the idea behind the criterion is very simple. You would want your complex saddle point background to be a reasonable background on which you would want to define a field theory. And that because the Euclidean action of the different fields involved is the path integral should be well defined. That restricts these saddle point geometries. And there's some evidence for this criterion. If you apply it and if you work it out for known saddle points, well, it eliminates certain pathological wormholes, and it does allow for other complex saddle points which we really want to be which we really think of are meaningful in a quantum theory, such as, for instance, the complexified Kerr solution, which perfectly fine explains its thermodynamic properties. So we decided, decided to ask the question, do the no-boundary saddles satisfy this new criterion? The no-boundary saddles in all these models of inflation that I discussed. So you might wonder, well, what can go wrong with these no-boundary saddles? They are certainly not the most exotic saddle points that we've heard about today or that have been considered. They're fairly straightforward saddle points in which you start with an approximate Euclidean de Sitter space, so in other words, an approximately four-sphere kind of solution that goes through a complex transition phase into a Lorentzian expanding universe. It's not very exotic, but it so happens that a strictly Lorentzian expanding universe is already just on the edge of violating that criterion that Kontsevich and Segal propose. And so it turns out that the way you approach Lorentzian classical cosmological behavior is in fact very relevant to this criterion. And so strangely enough, this criterion tells us something about the quantum corrections to Lorentzian behavior of the cosmological background. So it's a little bit mysterious to me why it does so, because these quantum corrections are buried in exponentially small deviations from just classical cosmological evolution, but it does. On the other hand, down at the bottom there of the figure, things seem fine, because the geometry is essentially Euclidean and the criterion is bound to be okay. So we ran all these models that Planck considered, that the Planck collaboration considered. We ran the criterion of consubstantial through this. We checked all those saddle points in all these different models, and we found, somewhat to our surprise, that the criterion selects those no-boundary saddles, those models of inflation, if you wish, in which the universe emerges on a concave patch of the scalar slow roll potential. If you translate that statement into a statement about observations, this is what you get. The red lines, so these are 9 or 8 different models of inflation, and I'm varying a parameter, so which in the potential, and the bands are between 50 and 60 e-folds. The red lines up there are excluded regions. So in other words, if you refine the no-boundary proposal with this additional criterion that your complex saddles should admit a meaningful quantum field theory, then you restrict the models of inflation that you can have in the no-boundary theory to those green bands. In other words, you predict that the tensor to scalar ratio of fluctuations should be less than 0.08, roughly. So that's the first result. Yeah, I can pause here if there's a quick question before I move on to the... Yes? Yeah, so these are 8 single field models with 1 free parameter that you're varying, yes. He was asking whether I was assuming single field inflation, and the answer is yes. I'm running these models essentially through my quantum cosmology machinery. Okay. Yeah, so the second part of my talk is connected, yet somewhat different. The second part is, again, this question, okay, can we make some headway on what are the microscopic degrees of freedom behind that path integral? Can we reformulate, can we rethink the gravitational path integral? Of course, the game in town there is to look for a holographic description. And in a sense, this picture sort of reveals already where I'm heading. And the goal of this second part will be just to explain this picture. That's a paper which came out last year with these 4 co-authors. Okay, so let's again have a closer look at these no-boundary saddle points. And let's consider the simple saddle point. Let's consider exact empty de Sitter space. In that case, the saddle point is a clean half force sphere matched on a sharp boundary onto an expanding branch of the Sitter space. So it's a sharp Euclidean Lorentzian transition, whereas this was a blurred transition in models of inflation. You can think of that saddle point. Well, its amplitude is given there. The wave function acquires a real part from integrating the action over the Euclidean part of the geometry, and you acquire a huge phase from integrating the action over the Lorentzian expanding part. So the wave function takes a WKB form in which our de Sitter space arises with a certain amplitude. Now you can think of those saddle points as complex solutions to the Einstein equations in the complex time plane. And if you think about it that way, what we have there on the left is nothing else but an integration from the south pole at minus pi L over 2 to the equator of the force sphere, and then up into a Lorentzian time direction to some final boundary. Very simple configuration. The metric is written on the top there. Now, let's look at an even more abstract and yet more fundamental quantity. Let's look at psi star psi in this way. Well, psi star psi, then the imaginary part essentially goes away, and you're left with just the Euclidean part of the amplitude. You're left with just the amplitude. In the complex time plane, this would be like not going vertically, but essentially it would be equivalent by integrating over the entire sphere. In the set, we have just a sphere. Psi star psi is a quantity which we may not consider physical at all, in fact, some sort of normalization maybe, but in fact it is capturing there in Euclidean terms, in purely Euclidean terms, it's capturing the de Sitter entropy, minus the action of Euclidean de Sitter space, minus the Euclidean action of the force sphere, is nothing else but the de Sitter entropy. So there's a connection between Lorentzian de Sitter space and the force sphere there. Now, I want to do the following. I want to calculate the exact same quantity, the de Sitter entropy, but going around a different way, going around from the south pole to the north pole of the sphere by going first up, then across, and then down. And the reason and of course I'm going to get the same result. But the reason I want to calculate it that way is that by going up and then down along these vertical blue lines, I discover that the very same saddle point has a different geometric representation in which it looks like a Euclidean anti-de Sitter space with an overall minus signature. And if I calculate the de Sitter entropy that way, I discover something interesting. If I go along the vertical line, the blue line, all the way up, you of course get the Euclidean anti-de Sitter action. That it means I get the deregularized Euclidean anti-de Sitter action and a bunch of counter terms. However, if I then go horizontally, what happens is that I get that the counter terms that I was getting in the vertical part are cancelled and replaced by a phase, also multiplying the counter terms. And then the second part of this action is just a complex conjugate. So at the end of the day, if I go around here, then my Euclidean de Sitter action is in fact written as -2, because I get two legs here, times the regularized Euclidean ADS action. So there's a natural connection at the level of the wave function of the universe, at the level of thinking about complex saddle points between de Sitter and anti-de Sitter. Whereas if we think classically about cosmology, you would have to come up with some sort of wacky continuation. If you think quantum mechanically about cosmology, then it all amounts to nothing else but a statement that complex saddle points, given complex saddle points of a path integral, have different geometric representations depending on which contour you choose. And so that's this picture. What we want to convey here in the picture in our paper is really, here we have the force sphere, but somehow, and the force sphere captures the entropy of Lorentzian de Sitter space, but somehow that entropy we can also think of as twice the regularized action of Euclidean ADS spaces emerging from these poles and then suitably identified. So in fact, yeah, this picture here, you would be following a kind of that contour. Why am I interested in doing this? Obviously, because once I have an ADS connection, I can use ADS CFT to replace the saddle point by a field theory on the boundary. And so we can add one more ingredient here to our chain of equalities. we started out thinking about the de Sitter entropy, relating it to the action of the force sphere, relating it to the regularized action of an auxiliary ADS space, but that regularized action of the auxiliary ADS space is in fact nothing but a logarithm of the partition function of a dual CFT on the S3 boundary. Where is the S3 boundary? The S3 boundary could be the boundary of these ADS spaces. Or if you wish, you could think of the dual field theory as living on these points. So now we arrive at the conjecture. We arrive suddenly at the conjecture that the de Sitter entropy should be given by -2 the logarithm of the partition function of a dual field theory defined on the tree sphere. So let's check it, because you should be very skeptical at this point. All I've done is I've played around with different geometric representations of a saddle point. So it looks like what I've done is very, very semi-classical. And this is what we thought. And of course, everyone knew already that the leading term, the semi-classical term, the pi over lambda term, matches between these two. So we must now specify, right? If we're going to check this conjecture, we must specify, we must embed our theory in a full 11D supergravity theory. We must identify an ADS-CFT pair, which I've done here by considering the ABGM dual theory, and so forth. Then you can calculate, then you can check it, because the partition function of the ABGM theory is known, and so I can calculate it. In fact, it's known, not just the leading order is known, but the whole series is known. This is the term which through ADS-CFT matches the Gibbons-Hawking entropy of the Sitter space. But there are all these corrections. And so a key question is, can we reproduce these corrections which take us beyond the saddle point approximation of the path integral? And so that's the calculation we performed in our paper. I refer you to our paper for the details, but it amounts to adding higher derivative terms to your bulk action and computing one-loop determinants around the saddle points that enter, so the S4 cross S7 saddle point now, using techniques developed by Sen and Barmanio 10 years ago. And the bottom line is that, in fact, both this correction and the logarithmic correction match exactly between boundary field theory and bulk. And that is a kind of striking result, because it means that for the first time we have a concrete proposal for the quantum corrections to the de Sitter entropy, and a vague idea of this perennial question: what does the de Sitter entropy actually count? A question which was open since 1977, and I think we have an answer. The microscopic de Sitter entropy does not quite count microstates. It's associated with the partition function of a holographically dual CFT defined on a tree sphere. There's no time and there's no Hamiltonian, and so it's probably a little too naive to talk about microstates. Also, the exponential of the quantity that we get out of that holographic field theory is not an integer, and so it would not really you couldn't say it's a number of microstates. But on the other hand, being given by a QFT path integral, the entropy does clearly represent some sort of measure of degrees of freedom, and likely some sort of entanglement of those degrees of freedom once we interpret it in the Lorentzian. What remains to be done? What remains to be done now is to extend that kind of holographic thinking about the no boundary wave function to include sources, to include observables, to calculate more tangible quantities that are relevant in cosmology compared to that abstract de Sitter entropy. So that's it. Thanks.
Okay, thank you very much for the nice talk. So we will take 5 minutes to exclusively ask questions about this talk, and then I will invite both of the speakers to ask questions and have discussions for both of the talks.
let me go to an inflationary model that has really de Sitter space in the early phases. There are plenty of them. Now I can compute what happens with the relative size of the tensor fluctuations. I mean, just relative size fluctuations divided by the homogeneous part of the metric. That's even a frame invariant quantity. That quantity increases when you go closer and closer to the Big Bang. Is that not going in the wrong direction, as when you say you want to start with a state that where the fluctuations do not matter? My impression is at least the tensor fluctuations, we can compute them and they get stronger and stronger. It's more the opposite, that the early universe may be fluctuation dominated.
Yeah, you must be working.
Observation. I mean, you can compute these fluctuations, of course. I mean, it's a standard computation of the tensor fluctuations, how they, the relative tensor fluctuations, how they behave when you come closer and closer to the Big Bang and they grow.
Well, they don't grow unboundedly, right? It's h squared.
I mean, if you go further and further back, they are getting bigger and bigger. Actually, they get formally singular at the Big Bang, a singularity. That's part of Staropinski's argument that there should be a real singularity. There doesn't have to be one, but it's certainly an observation. Also, people who mimic, you know, inhomogeneous cosmologies, they always find that if you go back, it gets more and more inhomogeneous.
Yeah, so that's not the case in the no boundary proposal.
So is that not in contradiction?
Oh no, not at all.
Why not?
Because you're not calculating, your story has nothing to do with the no boundary proposal.
No, but my story has to do with what we know that happens in inflationary models.
Classically,
know-
you're extrapolating classically.
Yeah, so I'm just saying, you know, the classical extrapolation goes in a direction that is completely opposite of your assumption. You may say, of course, that suddenly breaks down or something like that, but I make just the observation that a priori, if you just look at face value, you get the impression that when you go back in the inflationary universe, it gets more and more inhomogeneous.
It's not completely in contradiction, right? When I say that the fluctuations vanish, I mean the fluctuations vanish all the way at the bottom here. This is a region where the geometry, where the background is quantum mechanical. The typical size is that of the set by the scalar potential, so it's much larger than the Planck size. There you have, but in that complex region where you do the transition and where you start inflating, you just have your classical story. Your tensor perturbations are there, your scalar fluctuations are there. All I'm saying is that the classical extrapolation backwards at some point breaks down even at the level of the background, and that's where the no boundary ingredient kicks in. And that is indeed, of course, in this very earliest phase, a huge and strong and ad hoc a priori, perhaps, regularization of what otherwise would evolve into a singular state.
Let me
I
first
certainly
say-
agree that the no boundary proposal is a very strong theoretical ingredient or input that one puts there. Sure.
Let me just, I mean, I'm not saying that there is an absolute contradiction, but it's also not true that it's just classical. The two-point function of the graviton is, of course, a quantum object as well. So even in in simple quantum gravity theories, if they produce inflationary universe, you have a two-point function in the tensor sector that goes first to larger and larger values. I'm just saying it goes in a certain sense in the wrong way for you. You have to cut that off and say, I have a proposal where the beginning is completely different and I reach first very large fluctuations and then they become smaller. You know, for simplicity, it would be simpler if you would start with
Also-
a universe that is fluctuation dominated.
Also, your fluctuations start in the Bunch-Davies, right? You're assuming some sort
But
of
that is
state.
Bunch-Davies vacuum. The Bunch-Davies vacuum, you compute the tensor fluctuations and they grow if you go
Well,
towards
I'm doing
the Big
exactly
Bang.
the sorry, but I'm doing exactly the same. Hartle-Hawking implies Bunch-Davies on the fluctuations.
Okay, more
In
questions. We can
fact,
continue.
Bunch
this
Davis
also.
is sometimes called the Euclidean vacuum.
Do you agree that the tensor fluctuations grow in standard computations when you go towards the Big Bang in an inflation?
Not if you put them initially in the Bunch Davis.
Doesn't, I mean,
What you mean is some
all these calculations, these standard calculations, start formally with Bunch Davis, and then of course people say it's not valid for all the time and things like that. But there's a simple observation: if you take this standard approach, Bunch Davis vacuum, or just invert the propagator of the effective action, gives the same result. There's an observation that the tensor fluctuations grow when you go towards the Big Bang. I mean, you may agree or not agree to that, but that's the observation that everybody makes.
It's a useless discussion because we're saying exactly the same thing. You're saying the fluctuations grow when we go back to the Big Bang, and then all of a sudden, miraculously, they die to become in the Bunch Davis vacuum.
Your proposal.
No, that's your proposal.
No,
You
no.
also assume Bunch Davis.
I'm saying it's much simpler if the beginning of the universe is actually fluctuation dominated and not dominated by homogeneous
But
fields.
then you're not
Your
putting them in
proposal
Bunch
is
Davis.
that it's
But then you're not putting them in Bunch Davis.
So you are doubting that the tensor fluctuations grow when you go back? I mean, just take the standard calculations.
You're confusing classical and quantum behavior.
That's a statement about the propagator. That's not classical and quantum. I mean, the propagator is an object that exists in both. If you make a classical approximation or not.
Are you starting with Bunch Davis or not?
I'm actually, if you do the calculation with Bunch Davis, that goes back to Rubakov and so on.
I'm asking a yes/no question. Are you starting with Bunch Davis or not?
I can say I start with Bunch Davis. Actually, it's not the most elegant formulation, but...
so then we're doing the same thing, and the fluctuations will behave exactly the same. In fact, it's known
So
since
do
the
they
80s.
grow or not when you go towards the Big Bang or not in this type of inflationary cosmology? It's a very simple question. It's frame invariant. There exists plenty of calculations that find that actually the relative fluctuations grow when you go backwards, the tensor fluctuations. True or not true? This is not completely saying that something can happen differently at the very early beginning, but it's just an observation.
I'm saying that in the no-boundary state, the behavior of the fluctuations in inflation is just like the usual Bunch Davis calculations.
Which gives you growing tensor fluctuations. Sorry.
So we are actually well into the discussion time, so feel free to continue if you want. Okay, so the next question. So you can now ask also, I think, maybe you can go there. You can ask your own question. Okay, that's yours.
Can I ask my question?
Maybe after.
Okay, sure.
I have a question for the first speaker. I think it's a continuation of the question that was asked. I had a question. You were saying that you have a universal result for complexity, and my understanding of complexity is that it's a very usually ambiguous quantity, especially in field theory. Right, it's only well defined when you have a specific quantum information protocol. So, could you specify? So, you must be using a particular notion of complexity.
No, I'm just saying that the result is universal for a very specific state. So the state is firstly Gaussian, and so this is obviously very specific in field theory. And then I am considering a complexity between two regions which are separated by some causal horizon, and only then. For this long-range entanglement, which people have calculated the entanglement entropy corresponding to this kind of regions. And for instance, in the de Sitter case, that was computed by Maldacena and Pimentel. I'm saying that the complexity for such systems seems to be very universal in the sense that it's finite and it's independent of this Lagrangian. But this is obviously a very specific quantity. So I'm looking at the free scalar field, and then or free fermion field or something, and then also it's like a very specific Penrose diagram that I'm considering.
And you have a specific definition of what you call complexity,
I'm-
which I missed.
I'm using this circuit complexity, but for Gaussian states that can be defined less ambiguously, up to a cost function.
Okay, you
I-
want to continue?
I do have a question for the second speaker, Thomas, about something about the no boundary proposal. So you mentioned this Kontsevich criteria, which is in terms of the matter. But I thought my understanding was that when you have matter, somehow there's like two possible, ways in which you need to rotate in the complex plane, depending on whether you have a lot of matter or depending on whether it's pure gravity. Could you comment on that? Like if you use, if you use if you use the analysis of the saddle and looking at which branches you should look at. I thought you were part of that with Neil, right? You looked at this, or at least Neil Turok looked at these different. There's different type of saddles depending on the matter content. Like the different type of Lefschetz symbols you need to select.
Yeah, but that is more in some sort of Lorentzian kind of path integral.
Yes,
picture,
yes.
right?
If you start from. You're not.
No, I looked at this, but that's quite a while ago. I have nothing really to. What was the outcome of this whole thing? Let me think. I think Neil was looking for, or Neil was worried, right, that if you have a lot of matter, you could be picking up a different saddle in which fluctuations essentially would not be well behaved. Right. Since then, the picture has changed a little bit. So Neil was taking a kind of a path integral seriously, and he had identified an exponentially suppressed saddle, which, however, could become the dominant saddle when you had a lot of matter. Yes, exactly. But I think the lesson of holography is a little different. The no boundary proposal emerges from these DSCFT proposals, and it does so only with the usual saddle. And so I think you're gonna have to have, and this is what Neil had, a different theory of the path integral. He had a Lorentzian path integral in order to pick up those non-physical saddles or so. But this is really quite a while ago that I'm trying to remember.
You're saying it's different.
So
you're saying that the Lorentzian analytic continuation is kind of a
yes.
It's a different criteria than this
exactly.
Kontsevich.
So now I see
so that's what.
Now I see the confusion. Yes, what I was talking about here were different representations of the usual no boundary saddle point. What Neil was talking about was contours connecting different saddle points. So he was taking some sort of path integral contour much more seriously than I was doing here.
Okay. Shudo, you wanted to ask something?
For you? Okay. Which is, so you use this different representations of the contours and did some, so that picked up this ADA space, and then you went to the CFT dual. But is this CFT dual, can you relate this to the CFT dual to de Sitter directly, like a la Maldacena? And like, for instance, for this higher spin gravity, we know what kind of CFTs are. Is there some match there?
Right, that was the key point. The crux of the statement here is that it is in fact the same ADS-CFT dual that acts as the dual in DS-CFT. So we do holography as we usually do it. And the reason that we can do this is because the connection between de Sitter and anti-de Sitter is all in the counter terms, is all in the surface terms. Now you might say, well, wait, this is too easy. And indeed, it becomes more complicated when you consider the wave function with sources turned on, in the Hartle-Hawking wave function with a scalar field turned on or whatever. Then you could play the same game. In fact, the entire Hartle-Hawking proposal can be rephrased in Euclidean ADS-CFT language. It's in fact pretty much Euclidean ADS-CFT avant la lettre. But the sources that we're interested in cosmology, real scalar fields or infradon turned on, they will eventually translate into complex sources on the ADS side. So if you think about the ABGM partition function for various sources, a la Friedman-Pufu or whatever, we can evaluate those partition functions for real and complex values for those sources. And in ADS-CFT, we're always interested in the real values because that's what we compare with real Euclidean ADS saddle points. In DS-CFT, we're interested in complex values for those sources.
But maybe a quick follow-up is when you have the scalar field in say, de Sitter, there's usually like two operators which are dual to it, the two shadow operators, and that's the idea behind like having this entangled two CFTs to give de Sitter. So in this picture, but for ADS, like is there like similarly like two shadow operators? Two operators like this of dimension.
Oh, I see. I hadn't understood that's what you were doing. You're saying your left-right thing, right?
Yeah.
And you're saying that somehow the quantization condition is different on the left and the right? You choose a different...
Yeah, it's like just like the H plus and H...
Yeah. Oh, I see. Okay.
Is there something similar which emerges naturally in that case?
Okay, yeah, so of course I wondered about that in your talk as well. I don't immediately see it in the sense that if I were to evaluate my wave function of the universe in position space, then evidently it would be the slowest fall of that provides the argument of the wave function. Of course, I could be inclined to evaluate the wave function in momentum space, and then I probably would have to select the other thing. But we do not have this left-right thing. If anything, in this version of DS-CFT, the analog of the wormholes in ADS or the entanglement or whatever would rather have to do with the scry minus and scry plus. Okay. You see, we always have two saddle points and they come in complex conjugate pairs, and how are they connected? That is a tricky question.
I see. Okay. Thank you.
More questions?
Okay, for Thomas, just to clarify your results, if I take, say, my inflationary potential as m squared phi squared, for example, are you saying that's just forbidden by your underlying principles, or is it just that it's allowed but the prediction moved down in the NSR plane?
I'm saying right. If you were to fix the overall amplitude, then indeed it's ruled out. You don't get these 60 e-folds with this additional Kontsevich-Segal criterion applied to the saddle. Yes.
Okay, so it's sort of a sick theory in some sense, in your point of view.
Well, I applied this criterion just because I was curious, right? I'm not saying I understand what it does. But it's very fascinating because this Euclidean Lorentzian transition goes exponentially fast, essentially. They're exponentially small corrections to this Lorentzian background, and somehow this criterion picks that up and appears sensitive to what these precisely are. So it's clearly some sort of non-perturbative quantum gravity effect that the criterion captures. But why now m squared phi squared not, and the others yes? People familiar with the Swampland program in string theory may have noticed some sort of connection between these results and what the Swampland criteria tell us. Both sort of zoom in on concave patches of the slow roll potential. So that's, to me, the interesting thing happening here, that somehow this Euclidean quantum gravity framework, semi-classically, and swampland reasoning, completely different, seem to point to the same thing. There's clearly something to be understood there.
If I can just ask one related thing. So if I tried doing, say, m squared phi squared for phi a few m Planck, during regular slow roll inflation and then declared that the phi squared shape flattened or did something else, does it then obey these principles, or is it still forbidden?
Yes. No, then it will obey. Yes. So it's very sensitive. So it sort of connects the earliest phase, almost literally the boundary Euclidean phase and the late time behavior. That's what the criterion magically connects. And so if you change one, you will indeed,
More questions?
It's too bad that we come to this prediction now and not 10 years ago.
We still have some time, so don't be shy.
I guess we can be also slightly provocative. So, wouldn't you agree with the following statement that, okay, this Niels program or whatever, I mean, Niels was just one of the followers, and by using Lorentzian signature in the path integral should be what we mean by the definition of quantum gravity, and anything else should be an approximation, and maybe these Euclidean and these, Timballs and whatever, the saddle points, the dominate, the contributions, which obviously is along this Euclidean path, should be sort of telling us if you Euclideanize gravity, how much actually we can trust and how much we cannot. I'll just give you an example. I'm pretty sure if I do Lorentzian path integral on finite time interval, then the Euclidean approximation will have corrections to it that I can calculate. So do you have any comment on that?
Yeah, sure. I think that's right. Ultimately, the discussion with Neil a few years ago boiled down to a fundamentally different assumption on what's fundamental. He was taking the Lorentzian path integral very seriously, also for the cosmological problem, including the Big Bang. And we were taking the Euclidean viewpoint seriously as a starting point, motivated by DSCFT and holographic statements. And evidently, the debate really is, what do you do at the Big Bang? Do you close the past, or do you put an initial boundary? It's a little bit like that. Of course, the Lorentzian path integral is fine if you go from an initial boundary to a final boundary. This was, however, not the problem we were trying to solve.
Yeah, but I mean, don't you think that quantum mechanics tells us that there is a phenomenon of interference, just even for single particles, and that the laws of quantum mechanics are those, and observations are those that support these phenomena of interference, and unless I change rules of quantization in gravity, I somehow expect that the same phenomenon.
No, not at all.
No?
Usual quantum field theory comes out of this, of the Hartle-Hawking construction, right?
Yeah, but not
once
exactly.
you have a background and you have a notion of time, it's all the Schrödinger equation comes out.
Yeah, but only the low energy part. I mean,
Sure.
not all the excited states.
Sure.
I mean, not all of the structure.
All of the structure, as long as you have a classical background, which is what you're assuming. A classical space-time.
Yes.
Yes.
Yeah.
Everything else comes out. It's only when you're talking about having no classical space-time that Hartle-Hawking begins to differ from anything normal.
Okay.
Sure, you can have black holes.
Black holes, when you get close to the singularity, you don't expect to.
Well, that of course.
That you can do this mini superspace model. This looks.
Sure, that's a very interesting question, of course. Yes.
Highly. No, what I'm surprised that in this Euclidean approach, you use mini superspace model. You don't need to do the full path integral. And this is surprising that with this very sort of simple model, you're able to recover The question is, what would happen if somebody would go ahead and do the full path integral, let's say triangulations or something
Well,
like
yes and no, right? If when I was comparing the quantum corrections to the de Sitter entropy, which we were getting from the dual field theory, so in principle that is the full answer. When I wanted to redo that calculation on the gravitational side, working with the Euclidean saddle point, I had to include a higher derivative correction to GR, and I had to calculate loop corrections. So if you're gonna move beyond the semi-classical approximation, you're gonna have to include a lot of baggage. We were up there we were in 11 dimensions and everything, right? No, it doesn't remain
let's
just.
say you stay in 4 dimensions. Let's say you don't.
Then there's limited number of things you can derive.
I mean, you can do Reggie calculus, take triangulation, sure. And but then it's amazing that even in a Euclidean space, you just sufficient just to take the mini superspace model to give you more or less.
Yeah. So this goes back to the.
Although the question of black holes, I think you won't be able to play this game if you want to explain what's going on with the black hole. I think there you really need to do the full path integral.
Well, even there in the low D models, people have now, as you know, have found wormhole saddles that could become relevant after the page time and all that. In the last couple of years, the Euclidean quantum gravity framework seems to deliver their work exactly where you don't think it should be delivering. Why? I don't know. It seems to hold certain non-perturbative corrections to gravity in a fairly.
I mean, you're expecting to have a huge fluctuations in the regions of large curvature.
Sure.
So
It doesn't do that.
This sort of
no, I agree with that.
Small fluctuations should work.
So sure. Yes. The end of time could be very different from the beginning of time.
Or locally, if you're in black, you go toward the curvature singularity.
Okay, so I don't see any other questions, and we are at the end of the session. So before you leave, we have one announcement, but before that, let's thank the speakers and our technician.